Hello, this is Rick from MathX, and today we're going to be solving the number 22 from the AMC 12A Fall Edition of 2021. Now, this number 2022 is actually surprisingly free. Like, if you get to this problem during the test, you sit down during the AMC 12 and get to the 22, then you probably have the capability to solve this problem, because there are a bunch of problems before this from 1 to 21 that are way harder than number 22. As I'm about to show you, number 22 really just involves some basic casework where we only have to deal with 2 cases. But just in case that still scares you, I'm about to go over it step by step. So without further ado, let's just get into the problem. Azar and Carl play a game of tic-tac-toe. Azar places X in one of the boxes in a 3x3 array of boxes, and Carl places an O in one of the remaining boxes. After that, Azar places an X in one of the remaining boxes, and so on until all the boxes are filled or one of the players has their symbols in a row, horizontal, vertical, or diagonal, whichever comes first, in which case the player wins the game. Suppose the players make their moves at random, rather than trying to follow a rational strategy, and that Carl wins the game after he places his third O. How many ways can the board look after the game is over? So this problem's context is really simple. We have 2 dudes, Azar and Carl, playing tic-tac-toe, with Azar going first and being X'd, and Carl being our second, and they alternate from so on, just as like normal tic-tac-toe, and he's an O. And then it literally uses 3 lines in the paragraph to explain the basic rules of tic-tac-toe, which I don't think I need to go over. And it's trying to understand how many different configurations will the board look. Another good thing worth noting is we don't have to care about rational strategies and all, because that would make the problem like way harder. So we can just think about like the physical configurations about what the tic-tac-toe grids will look like. And we just need to figure out how many configurations there are, such that Carl wins the game after he places his third O. So if he places his third O, that means that Azar before him would have had to also have placed his third X. Because remember, Azar is going first and Carl is going second. So in order for Carl to have placed his third O, the sequence would have had to gone like XO, XO, XO. So third O, that means 3 X's are falling before. However, since Carl is the one winning this game, that means that Azar's previous 3 X's could not have won. They would not be in a row, vertical, or diagonal. So this kind of gives us some clue on how a physical grid would look like. However, it's still really useful to draw out one such example. So I'll do that. So here is my gorgeously drawn tic-tac-toe grid. So now let's start putting some symbols, some X's and O's, in the cells in this grid to understand what a board would look like. So since we know that Carl wins, we can just choose to put 3 O's in a row. So you know what? I'll just put it like this. Make my things extra big because we want to have big symbols. So we're going to have Carl win this middle row like this. And then we know that we have to put 3 x's for Azure. But here's the thing. We can't put 3 x's in a row, because that would have meant that Azure would have won, and then for some reason, Carl would have kept on playing. We need to place 3 x's such that it won't look like Azure had won already. This can be done by putting these 3 x's in any of the 6 cells, as long as they're not the top row or the bottom row. So the number of ways that we could put these 3 x's in the remaining 6 cells would just be 6 choose 3. So that's the total number of way we could put 3 x's in these 6 cells. We're going to just take 6 of these cells and just choose 3 of them to put the x's. However, we have to subtract the cases where it looks like Azure has won. And there are only 2 such cases for that. If Azure gets the top row or Azure gets the bottom row. So it becomes 6 choose 2. 6 choose 3 minus 2. Now doing some quick maths, we get that 6 choose 3 is simply 20, and 20 minus 2 is 18. Now, for those of you who just want me to elaborate further, 6 choose 3 is just 6 factorial by 3 factorial, 3 factorial, and just canceling out the 3 factorials and then canceling out another 3 factorial from 6, we get 5 times 4, which is 20, which we subtract from 2 to get 18. So just elaboration on the quick maths. But basically, the point is, in this configuration, we get 18 possible ways. Okay, that's nice, but what are we going to do about every other configuration of a tic-tac-toe board? Well, here's the thing. We can actually say that a lot of the other configurations will just, even though they won't look the same, they'll behave the exact same as this current configuration. For example, if I literally take this 3x3 grid, for example, by copying and pasting a new version of our original 3x3 grid, and just by messing around and seeing what would happen if we just put a row or a vertical column in another set of squares instead of just the middle row. Let's just say I do the exact same thing, put 3 in a row across the first vertical column, like this. Then we see literally the same counting problem arise again. We need to pick 3 of these cells such that Azar does not win with his 3 x's. So no 3 x's are in the same row. So once again, we can take 6 of the remaining squares and choose 3 of them to get the total number of ways to put 3 x's in 6 cells, and then we can subtract the 2 cases where Azar wins. So if all the x's are in this middle column, or all of them are in this end column. So we see that this computation for our first case can be applied to a bunch of other cases. So if we just iterate through that, the cases, all possible cases, we can multiply this 18 by the number of other identical cases to these two. So we've already discussed here, but this configuration can be applied when Azar wins in any row or any column. So since there's 3 rows and 3 columns, that gives 6 configurations, each of which have 18 possible solutions. So we can take our initial 18 value for this tic-tac-toe grid and multiply it by 6, because there are exactly 6 other configuration of Carl's O's which will yield the same counting problem. So we have 18 times 6, which once again, just doing some easy computations, we get 108. But here's the deal. At this point, we still haven't dealt with a fundamental part of tic-tac-toe. And that is getting a diagonal win. So let's just draw one example. Okay, so here is my slightly less gorgeous grid, but still great grid. And in this, we're going to set it up as if Carl wins by placing his third O along a diagonal. So we're going to pick the upper left to down right diagonal, just because I want to. Doing this, we see that no matter which three cells we pick for Azar to put his three X's, there is literally no way for him to win. So instead of subtracting 2 like we did in the previous cases, we can just count the number of ways for Azar to put his three X's by just looking at all 6 of these cells and choosing 3 for Azar to put his X's in. So this computation just becomes 6 choose 3, which I already computed for earlier to be 20. And without loss of generality, this counting argument can be applied when the diagonal goes the other way. So each of the 2 diagonal cases will have 20 different ways. And since there's 2 of them, we can multiply 20 by 2. So this gives us a total of 40 different ways to count for if Carl wins with his O's along a diagonal. So counting up these 2 cases, the 40 from if Carl wins along a diagonal, plus the 108 from if Carl wins along a row or column, we get 108 plus 40 to be 148. And then we just circle that answer and move on. So as you can see, this problem is really simple for a number 22 on an AMC 12 problem. Honestly, if you made it this far into the test, you probably should have solved this problem, because as I've shown you, I've just used basic casework and combinations. Nothing too crazy, especially at a number 22 on an AMC 12 example, level. This is relatively low level for an AMC 12 test. So this just shows, even though for the most part AMC problems are ordered from least to most difficult, it's sometimes worthwhile to skip around, because that's not always the case, and there could be problems at the end like this which are just surprisingly easy to do. So I hope you learned something, and see you in the next video.